Our mission is to build a larger scale fault-tolerant quantum computer to solve some of the most challenging problems that humanity is facing. We're building a superconducting-based quantum computer, but our qubits are different compared to traditional transmit technology. We're working on a technology, qubit technology, that has some fault tolerance built into the hardware. That will help us to really build a useful computer with much less overhead, fewer number of qubits that otherwise would be possible. What we're trying to do is to be more smart about the qubit architecture to make sure the hardware at the core is resilient against noise and error. That would give us a hardware efficient approach to build a quantum computer with far fewer qubits than otherwise.
Here at Anyon, we have ambitious goals in terms of developing large-scale, fault-tolerant quantum computers that have a number of commercial applications. To reach these lofty long-term goals, we've broken this down into a number of short-term milestones and also have integrated a certain amount of flexibility in our roadmap to make sure we're always working on the right problems. One of the advantages we have here at Anyon is that because we're a vertically integrated quantum computing company, we're able to take a systems engineering approach to build these quantum computers. And so because we build our own cryogenic systems, our own control electronics, we develop our own novel qubits, we're able to integrate all these aspects into a package that really works and is deployable in client environments.
Anyon is so unique because it brings the physics, the nanofabrication, the software, the cryogenics, and the testing within the same vertically integrated workflow. So in the nanofabrication, we're able to close the loop between the design, the process development, and the testing in real time because everybody is within the same team, within the same group, within the same building, and we meet each other every day. There's only a few environments like this that offer this depth of technical knowledge and scientific knowledge and still be result-driven like Anyon is.
Some of the key challenges in going from lab prototypes to client-deployed devices are really related to the robustness and the consistency of these systems. And so when we're talking about the cryogenic systems, there's a lot of mechanical parts that need to operate consistently over very long periods of time. Quantum system itself is a very sensitive system inherently, and so designing the systems to provide resilience against external environmental factors is very important.
What makes Anyon Systems very unique is the way that we approach the challenge of building a fault-tolerant quantum computer. That's why we chose our core technology, thinking of the fact that we would have to beat the speed of a classical supercomputer. And to our own opinion, this technology is superconducting qubits. We try to come up with architectures that will have some sort of protection against types of errors. We call that the hardware efficient approach. So these superconducting circuits will be a little more elaborate than simple transmons or fluxoniums, for example. And they will provide some sort of protection against noise and errors that will allow us to rely less on error correction codes afterwards. And we also want to manage to perform gates in a way that preserves that protection so that all the processes and all the computation remain in that noise protected state.
The fabrication processes that are the most critical to achieving high performance quantum processors are the thin film fabrication processes because the interfaces are so critical and create losses. The surface defects as well are all important. So the only way to achieve that is going to be to control all these parameters, knowing that you won't see the performance in situ. You'll have to implement different controls at different levels and monitor all the process parameters very carefully to achieve that.
For a company like us, it's really important to be able to control as well as possible the fabrication process. And that is why we are in the process of establishing an industrial-grade quantum fabrication facility with some partners so that we can have full control over the recipe and we can achieve the best materials possible.
In the next 5 to 10 years, we'd like to see the company building this technology into a larger scale machine that is deployed into data centers, especially sovereign AI data centers across the world, to the hands of the users. We'd like to see them do useful stuff with it and take it from there. That's the mission, and we look forward to building that technology with a new cohort of talents.